Mr. Geyser here with the second video in our Lesson 7a series, where in this video here, we're taking a look at 3 examples that are simple harmonic motions. A simple harmonic motion, or an object, is in a simple harmonic motion if and only if the distance from the origin d and time t is given in one of these 2 equations. Now, it's going to be very rare that we need to find one of these equations based off of a graph. Rather, we'll be told explicitly that some object is in harmonic motion, and we're able to use those 2 equations to help us solve that problem. To break down both of these equations here, they both have this amplitude, the maximum displacement of the object from its rest position, while the period is the motion is 2 pi over omega, where omega is greater than 0. Now, the period gives the time it takes for the motion to go through one complete cycle. This may not be one complete wave, but one complete cycle of some kind. The motion has a frequency, where it's omega over 2 pi, where again, frequency is just the number of oscillations that occur per unit of time. Speaking of oscillations per unit of time, let's take a look at the frequency of example 3, where in example 3, a point on the tip of a tuning fork vibrates in a harmonic motion, described by the equation of d is equal to 12 times sine of omega times t. We want to try and find omega of a tuning fork that is known to have the frequency of 386 vibrations per second. We can use 2 pieces of given information to help us find omega. That first piece of information is knowing that the frequency is just omega divided by 2 pi, and that we have a frequency of 368. When we have that equation there, we're able to manipulate it to try and solve what our omega is. We're really just dividing 2 pi, or multiplying 2 pi to both sides. And then we end up getting omega is equal to 772 pi per second. The reason why we're going to keep that pi there is so it stays inside of radians for us. That there is our answer for this problem, where the actual equation is just d is equal to 12 sine of 772 pi times t. For a moment, I do want to stick on this b value to try and look at it in context of frequency and period. For this b value here, or omega, this value has a direct relationship to frequency and an inverse relationship with period. Meaning, as b increases, frequency increases, but period drops. As our omega, or our b value, decreases, our frequency decreases, but our period increases. The length between the start and the finish of a wave increases as our b gets smaller and smaller. So if we look at the context of frequency, if we want to have a condensed frequency, we can say that in a single second, we can have 18 waves. It's a pretty condensed kind of waveform. But for frequency, we're really looking at waves that have like 90 waves a second, or 380 waves a second. And it's really difficult for us to analyze any 5 key points from these waves. However, instead of analyzing these waves, what will help us when it comes to these kind of problems is understanding the physics when it comes to these tuning forks. For this physics here, all I want to try and showcase is that for these tuning forks, it's just compressing the median of air to have this sound wave pass through it. When it comes to compression, notice that these 3 red points here aren't actually moving through the wave. They're just having them compressed and expanded throughout time. The wave itself for sound problems, or sound harmonics, is higher compression is higher maximum. Larger expansion or more volume is going to be one of these minimum values. The distance between these 2 compressed sections is the wavelength, or the period, of that function. At this point here, this is not the only type of physics problem that we will be solving inside of AP Pre-Calculus. One of those types of problems is this ball and spring in example 4. In example 4, a ball is on a spring and is pulled 6 inches below its rest position and then released. The period from the motion is 4 seconds. We want to try and write the equation for the ball's simple harmonic motion. To try and put some pictures and context into this problem, imagine that we have some ball that's on a spring that's simply at rest. However, as we pull the ball down about 6 inches, we then release it when it's at the bottom, when it's fully stretched of its spring. Once we release that, it goes up and then down and then up and then down, and we're able to use that kind of motion to create this sine wave over time. From this sine wave here, we're able to identify that the period itself is just going to be 4 seconds. Our A value, or our amplitude, should be about 6 seconds. And since we're starting at the very bottom of this minimum value, we know it's going to be a cosine function. Since we know it's going to be cosine, we just need to plug in that A value and that omega value that we can solve for. A is really easy, plugging in that -6 because we're starting at the bottom and going up. This here happens to be our period, so we can say our omega is going to be 2 pi divided by 4, where our omega is just equal to pi over 2. For these kind of problems here, we'll be analyzing these physics-based problems, and it helps to try and visualize why these are harmonic functions, rather than just trying to pick apart what value we need to find the answer. Our final physics problem that we'll be exploring today is example 5, where in example 5, a mass oscillating up and down on the bottom of a spring, assuming perfect elasticity and there's no friction and there's no air resistance, can be modeled as a harmonic motion. If the weight is displaced a maximum of 4 centimeters, we want to try and find the modeling equation if it takes 3 seconds to compute 1 cycle. Assume that the object starts at rest. Now there's a lot of information here. I do want to try and break it down into 4 easy steps. The surprising thing is that this last sentence, assume the object starts at rest, tells us 2 big important things. 1, since we know it's starting at rest, we know that t is equal to 0, or it's on that y-axis. And since we're starting at rest here, we're going to be using that sine model. It's not starting at a maximum or minimum, like that previous example we showed, but we're starting at rest. Now, since we're able to try and grab this information from assuming the object starts at rest, we can also grab the information of 4 centimeters to help us with our amplitude, and this B value of that period of 3 seconds to help us find that omega value of 2 pi over 3. With that B and with that A there, we're now able to create that equation of d of t is equal to 4 times sine of 2 pi over 3 times t. For these 3 physics problems here, these are the types of problems that we're looking for you guys to try and solve on our AP test. Try and analyze these problems, drawing pictures, or visualize it in some real-world way to help you answer these problems. Thank you very much for joining us, and if you have any comments or questions, please leave them down below. I look forward to seeing all of you guys in that next video. Take care.